Hi, in this presentation I will show how to solve the longest common substring problem in linear time. First I will formalize the problem, then I will explain briefly what is a suffix tree and what is suffix array. Then I will show briefly how to solve the problem using suffix trees. But the main content of this presentation will be focusing on suffix arrays, so I will show how to solve this problem using suffix arrays. And later I will explain the suffix array, what are they, how do they work, and how do we construct them in linear time. And I will also explain about how to construct the LCP arrays in linear time as well. So what is the longest common substring problem? Suppose there are two strings S1 and S2 of size n combined. We have to find the longest common substring S in linear time. We can see this in this example. Suppose that S1 is AX BA BAX and S2 is ASD BA BAL. So the common substring in this case will be the longest consecutive set of characters BA BA and BA BA here. So this problem can be solved in linear time using either suffix trees or suffix arrays. The suffix trees, there are many algorithms to do this. One of the popular ones is called Euclidean algorithm. But there are more modern solutions which are considered to be more efficient using suffix arrays and LCP array. So the problem becomes how to construct these data structures in linear time. So the primary focus of this presentation will be how to construct the suffix arrays and LCP array in linear time. And we won't focus on the suffix tree algorithm because modernly most people are using the suffix arrays and LCP approach. So what is a suffix tree? A suffix tree is a tree that encodes all the suffixes of a certain text. So we start with the node and then we have a different set of edges. Each edge will correspond to the starting characters of a set of suffixes. For example, the first edge corresponds to all suffixes that start with the character A. And then we will have a different branch to correspond to a different possibility. For example, the first suffix is A, and then we can see a branch with a label of $1. So that corresponds to the suffix $. And then we at the leaf node we see a number. This number corresponds to the offset of the starting character of this suffix. Another possibility is AB. Then we have two branches corresponding to two different possibilities. So the first branch in this case will be $, which is, if you look at this text, it is ABBCA, and it has also a number 4, which means this suffix will start at the character 4. The other possibility is ABCABBCA, which corresponds to the whole text, and the offset in this case is 1, which means the suffix starts at the letter of position 1. So usually this data structure is not exactly like that. It has more optimization to make it more efficient. For example, the labels are not represented exactly in a set of characters. They are usually represented with a pair of numbers, the start and the starting position and the ending position, to make it linear in space as well as construction. And to use this data structure will be used in the suffix tree algorithms. However, we usually use another data structure, which is the suffix array. It is used in the modern solutions to solve the longest common substring problem. So what is the suffix array? A suffix array by definition can be obtained from the suffix tree. However, usually we will not construct first the suffix tree to obtain it. However, by definition, we will only see how it can be obtained. So the suffix array contains the sorted array of all the suffixes, and this number is corresponding to the offset of the starting suffix. So as we can see, in the first position, we can see the first suffix is a b b c a dollar, and then in the next position will be the next suffix that comes in the lexicographical order. So we can see the first two characters are the same. However, the third character is the one that comes after the third character here. So this array is sorted in the lexicographical order, and we will see later how it can be used to solve the longest common substring problem. So how do we solve the longest common substring problem using suffix trees? Suppose that we have two strings x and y. The first step can be to set a string s by combining the two substrings. What we do is we usually insert a certain character between the both strings to signify the end of the first string, and the dollar sign at the end of both to signify the end of the second string. This usually can be a hashtag or any other character that is like not in the alphabet. So if x is xa bxa and y is ba bxba, then the combination of the two strings will be this string. Um, so what we do next is we construct a suffix tree using this string, and then we label each node as so this is the resulting suffix tree. What we do next is we label each node as as its children are are corresponding to the suffixes of x or suffixes of y. So we usually start in the bottom. Let's say we take this node since it has two leaf nodes. So the first leaf node out of this children are a hashtag BAXBA. So this one will belong to suffixes of x since it starts with a character of x and ends in y. The second one doesn't start with a character from x, it only starts with a character from y. So this one will belong to y. So since one of the children is x and one of the children is y, so this node will be xy. Let's take this node as well. We see two children. Both children contain a hashtag character, which means both suffixes start from a character from X. So this node will be labeled as X. And we take, for example, this node, since both its children doesn't contain the hashtag character, so the suffix will start from a character from Y. So this can be labeled as a Y. So what we do next is we find the deepest node that is corresponding to both x and y, and this one, but what we mean by deepest node is that it contains the longest sequence of characters. So in this case, when we find a deepest node labeled as xy, that will be corresponding to the longest common substring. In this case, the longest one can be seen as this one. It contains three characters, A, B, X. So this one is so ABX is the longest common substring. If we go back to this to verify, so we can see clearly ABX here and ABX here is the longest common substring. So how to solve this problem using suffix arrays? Most algorithms using suffix trees can be solved using suffix arrays along with another array. In our case, this array can be LCP. Um, so the length of the longest common substring will be the largest element in the LCP array, as we will see later. So in the remaining of this presentation, we focus on how suffix arrays and LCP arrays can be constructed in linear time. So how to construct a suffix array in linear time? Unfortunately, this was not always possible, as this remained an open problem for almost 10 years. and there were many attempts to do this. One of the attempts was able to achieve it in n log n time. So let us first define what is a generalized suffix array. It is a suffix array that contains a strict subset of all suffixes in array S. So basically it considers only a small amount or a small subset of all the suffixes in S. For example, the suffixes at even or odd positions. And this was used by an example attempt that was able to construct the suffix array in n log n. So it constructs two generalized suffix array. The first one considers the suffixes at odd positions in the text array. So for example, if this is the text array, then we only consider suffixes at positions 1, 3, 5. And the second one considers the positions at even positions. So for example, suffixes that start in position 2, 4, 7. So after obtaining two generalized suffix arrays recursively, we still have to merge them, similar to what we do in the merge sort algorithm. And to be able to merge, for example, two suffix arrays, we will have to compare two elements at once. So to compare two elements, an element here is a suffix. So for example, let's say this is a suffix and this is a suffix from the second generalized suffix array. To compare these both, we might need to compare n characters in worst time, n characters which is the length of the text here. So if we want to compare n elements and we have in worst case we need n comparisons for each comparison, so that means we have O of n square complexity in total. So a lot of work have been done to improve this, and a lot of smart solutions was able to improve this to n log n. However, the choice of the generalized suffix array is very important in determining what is the best solution that can be achieved, as can be seen in the next slide. In 2003, multiple algorithms aiming to construct the suffix array in linear time were published. One of them is called the Karkanen and Sanders solution. This one is considered to be the most elegant one out of those that came out at the same time. So, like the previous approach, it constructs two generalized suffix arrays, and then a merge operation happens. The difference here is that the merge can be done in linear time, and the novel idea of his work is on the choice of the two generalized suffix arrays, where the first one will consider suffixes that start at positions 1 or 2 mod 3, and the second one will consider those that start at 0 mod 3. We also use a rank function where rank of j will denote the positions in the generalized suffix array of the suffix j. The time complexity can be calculated recursively as T of S is the time of constructing the bigger generalized suffix arrays plus the merge operation, which we will see later that can be done in linear time. So now we will discuss how to get the two GSAs. The first GSA for the set 1 or 2 mod 3 positions can be done recursively in linear time. Once it is computed, it can be used to compute the other GSA, which is the 0 mod 3 positions, in linear time as well, but it is not done recursively. So to do this, we can form a two-symbol string SI rank I plus 1, where SI represents the characters in the second GSA, or the GSA with 0 mod 3 positions, like 3, 6, and 9. And rank I plus 1 is the rank of the character in the next position. So the rank I plus 1 can be obtained from the first GSA, since it is supposed that it is calculated at this stage. For example, if we have the, the, the position 3, then the rank of the next position can be obtained from 4, which is already computed in the first GSA, which represents the 1 or 2 more 3 positions. So as an example, if we have D3, A4, D2, A1, C7, A5, and A8, we can do a lexicographical sort on this array using radix sort. We obtain in this case A1, A4, A5, C7, D2, D3, D8. So this will represent the, the second GSA. We can keep track of each character and the position in the original text array to construct the second GSA. So now that we have obtained both GSAs in linear time, all is left is to do the merging in linear time as well. Now suppose we are at a point where we are comparing a character I from the first GSA and J from the second GSA. If they are different, we are done. We simply take the smaller one. However, if these characters are the same, we must compare the characters at positions I plus 1 and J plus 1. If they are different, we are done. Otherwise, they will belong to the same GSA, so we already know which suffix is lexicographically smaller, so each merge operation will take at most 2 comparisons. For example, if we are considering suffixes in positions 5 and 9. So if these characters are the same, then we can compare the characters in positions 6 and 10. If they are the same, we compare the characters in positions 7 and 11. However, here characters in 7 and 11 both belong to the first GSA, which represents the 1 or 2 more 3 positions, and we already know their order, so we are done. So this took at most 2 comparisons. So all of the comparisons in the merging operation will take this amount of comparisons. So it is considered linear time to do the merging operation. So in total, constructing the suffix array will take a linear amount of time. So now we will talk about the LCP array. Suppose this is the suffix array, and these are the corresponding suffixes. The LCP array will store how many common elements between the prefixes of 2 consecutive suffixes in the suffix array. The LCP value for the first suffix is 0 by default. Then, if we compare the first 2 consecutive suffixes, we can see that they have 2 common elements in their prefix, so we store 2 as LCP value. If we consider the second and third suffix, we can see that they have also 2 common elements. For the third and fourth element, they do not have any common elements, so we store 0 as their LCP value, and so on. However, this is not the way that we construct an LCP array, as this will cost n square. We will see later how can this be done in O of n time. So now I will state some facts, lemmas, and theorem that will help us construct the LCP array in linear time. So the first observation, we can see that the LCP between 2 suffixes is the minimum of the LCPs of all pairs of adjacent suffixes between them on the position array. So for example, if we take, for example, this suffix, and we consider all the adjacent suffixes on the position array, for example, this is the first LCP value, this is the second LCP value, this is the third LCP value. The minimum is 0. So, so the LCP value between this suffix and this suffix is 0. And to verify this, the number of characters that are common in the prefix of these suffixes is 0, since we have here AB, and here we have here we have B. So this implies that the LCP of a pair of adjacent suffixes is greater than or equal to the LCP of a pair of suffixes that surround them. So here the LCP between y minus 1 and y will be greater than the LCP between any 2 any two suffixes that surround them. So x should be less than y and z should be greater than y. So when the LCP between two adjacent suffixes is greater than 1, then the order of these suffixes will not change if we delete the first character of each suffix. For example, if we take here these two suffixes, they have an LCP of 2, which is greater than 1. If we delete the first character, which is in this case A, and in this case A, then these two suffixes will preserve the same order in this case, which makes perfect sense, since LCP is considered the number of common elements between the prefix of the two adjacent suffixes. So from the previous fact, we can see that if we move to the next position in the text array, then the LCP between those two elements will be 1 less than the LCP between the uh, consecutive suffixes in the suffix array. So, for example, here, if we move to the character B in this suffix, and we move here to the character B to this suffix, the LCP between those two suffixes will be 1. 1, which is 1 less than the LCP between the two adjacent suffixes, which was 2 in this case. The problem now becomes how to compute the LCP between suffix AI and its adjacent suffix on pose array when the LCP between AI minus 1 and its adjacent suffix is known. To do this, we will use the following notation to make things easier. We suppose that P is rank I minus 1, Q is rank I, J minus 1 is pose at the index P minus 1, and K is pose at the index Q minus 1. So the problem becomes how to compute height of Q when height of P is given. So with all these notations, it's difficult to see how things look in the position array. So we will take a look in the following figure. The suffixes are arranged in the ranks. Here we have the two adjacent suffixes at rank P minus 1 and P. Their position is J minus 1 and I minus 1. And here there are the two adjacent suffixes at ranks Q minus 1 and Q with positions K and I. So what we want to compute is a height of Q, which means the LCP between the suffix at rank Q and the suffix at rank Q minus 1, knowing the height of P, which is the LCP between the suffix at this rank and the suffix at the previous rank. So lemma 3 says if height P is greater than 1, then height Q will be greater than height Q minus 1. If we want to see it on the figure, it is here. If height P is greater than 1, then height Q will be greater than height Q minus 1. And from lemma 3 and the previous facts, it can be shown that if height P is greater than 1, then height Q will be greater than height P minus 1. So from theorem 1, we can see that when the LCP between AI minus 1 and its adjacent suffix is H, then the LCP between AI and its adjacent suffix must be at least H minus 1. So to calculate the LCP between AI and its adjacent suffix, it's sufficient to compare the characters starting from the H position. So to calculate the LCP array, we don't need to compare all characters between the suffix and its adjacent suffix in position array. It's sufficient to go through all suffixes in the order using the below algorithm. So let's check now how does this algorithm work. First, we calculate the rank matrix from the position matrix, and then we go through the elements of the rank matrix from 1 to n. So let's suppose that I is currently in this position. Then we check rank of I, which is P in this case, if it's greater than 1. If it's greater than 1, then we calculate the position of rank I minus 1, which is p minus 1. So position of p minus 1 will be in this case g minus 1. Then what we'll do next is we start from h equals to 0. So basically the position here corresponds to the character a because h is 0, and the character a also in the in the element in the suffix which with rank p, also character a. So we keep incrementing h until the characters no longer are equal. So h will be in this case 2. And then after that we set the rank of I to h, and we go to the next I. So the next I in this case, let's suppose it will be here, and then we calculate the rank of I, which will be q, and we see if it's greater than 1. If it's greater than 1, we calculate the position of q minus 1, which will be k. Then we start with h1, since in the previously h was 2, then we decremented it by 1. So we start comparing the elements starting from the position 1, and we keep incrementing until the elements are no longer equal. So here, uh, starting from j plus 1, sorry, starting from I plus 1 and j plus 1, we see that the elements are no longer equal. So we can set the rank, the height of q to the h finally. So now we'll analyze the time complexity of the LCP array construction algorithm. Since the time complexity is proportional to the innermost loop, and h cannot increase more than n, and in line 12 h decreases by 1 for every I, so h will decrease by most n, so h will increase by most to n, so the complexity of this algorithm is linear. These are the references used for this presentation, and thank you for listening.